The Andromeda system has played a pivotal role in reshaping our understanding of the universe and our place within it. For instance, our galaxy, the Milky Way, is part of a larger cosmic structure, and the closest galaxy to us is the Andromeda Galaxy. There are roughly 100 billion galaxies in the observable universe, and Andromeda was one of the key pieces of evidence that helped shift our perspective away from the Earth-centered view of the cosmos. This discovery challenged the belief that the Milky Way was the only galaxy in existence, suggesting instead that we are just a small part of an immense universe. While we've gathered much knowledge about Andromeda over the past century, much of it came from observations made from Earth. However, with the advent of advanced tools like the James Webb Space Telescope, JWST, our understanding has dramatically evolved. Recent data from the JWST has overturned previous assumptions about the Andromeda Galaxy, raising new astronomical questions that need to be addressed. The JWST has even detected mysterious signals from this neighboring galaxy, leaving the scientific community both amazed and perplexed. Throughout history, our view of the Milky Way has changed as our understanding of the universe has deepened. Initially, when our technological capabilities were limited, the Milky Way appeared as a faint band of light across the night sky, inspiring various myths and interpretations. It was often seen as a central and magical element in the cosmological beliefs of many cultures. As scientific knowledge progressed, especially with the invention of telescopes and the work of astronomers like Galileo Galilei, we began to understand that the Milky Way is not just a celestial phenomenon but an immense collection of stars, planets, and other cosmic objects. In the 1920s, American astronomer Edwin Hubble made a groundbreaking discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Hubble observed distant nebulae beyond the Milky Way and concluded that these were not part of our galaxy but entirely separate galaxies, each containing billions of stars. One of the closest of these galaxies was Andromeda, also known as M31. Andromeda has a long history of observations, dating back to the 10th century when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud in his star charts. Al-Sufi's observations are significant because he identified this distant celestial object without the aid of telescopes, relying solely on his keen eyesight. In 1612, Simon Marius provided a more detailed description of Andromeda based on telescopic observations, laying the groundwork for future studies of this vast galaxy. Later, in 1764, French astronomer Charles Messier catalogued Andromeda as M31 in his famous Messier catalogue, though he mistakenly credited Simon Marius with its discovery. Despite this, Messier's work helped make Andromeda widely known. For nearly a century after these observations, astronomers around the world worked to uncover more about this mysterious galaxy, each contributing to the collective body of knowledge. In the early 17th century, Galileo Galilei revolutionized our understanding of the Milky Way by using his newly invented telescope. His observations challenged the prevailing geocentric model of the universe, showing that the Milky Way was composed of countless stars rather than a nebulous cloud. In 1750, English astronomer Thomas Wright proposed a new theory about the structure of the universe. Wright suggested that the Milky Way was not just a random scattering of stars but a flattened disk of stars, with our solar system residing within it. While this theory advanced our understanding of the galaxy's structure, it was still limited by the observational technology of the time. A significant leap forward in our understanding of Andromeda came in 1864, when British astronomer William Huggins made a crucial observation. He studied the spectrum of light from Andromeda and found it to be different from that of a typical nebula, providing strong evidence that it was a galaxy in its own right. This discovery was pivotal in allowing humanity to grasp the true nature of Andromeda as a separate galaxy, not just a distant cloud of gas. Today, Andromeda is recognized as a massive galaxy, with a mass estimated to be between 1 and 2 trillion times that of our Sun. This makes it a colossal cosmic structure that resides relatively close to us in the vastness of space. Andromeda's history is also intertwined with theories about its formation. Astronomers believe that the galaxy is about 10 billion years old and that it may have formed through the merger of several smaller protogalaxies. This suggests that over billions of years, smaller cosmic entities gradually merged under the influence of gravity to form the grand Andromeda Galaxy we observe today. Galactic mergers are common events in the universe and play a crucial role in the formation and evolution of galaxies. For a long time, scientists believed that Andromeda was significantly larger than the Milky Way. This misconception was understandable, given the limitations of the observational tools available at the time. However, with the advanced technology of the JWST, astronomers are now able to study Andromeda in unprecedented detail, continuing to expand our understanding of the universe and our place within it. Heavenly bodies with ring-like structures, such as ring galaxies, captivate astronomers with their stunning features. These rings are composed of bright, young blue stars, while the central regions contain minimal glowing matter. These unique characteristics make ring galaxies stand out among the vast variety of cosmic structures. There are three main types of optical ring phenomena: atomic rings, inner rings, and outer rings. Atomic rings are located near the center of a galaxy, while inner and outer rings are positioned slightly farther out. Ring galaxies are classified into two primary types: O-type and P-type. O-type ring galaxies have partially located cores, with smooth, well-defined rings. P-type ring galaxies, on the other hand, have off-center cores, and their rings tend to be more irregular in shape. These ring systems are considered rare, with only about 1 in every 10,000 galaxies exhibiting them. Astronomers proposed two main mechanisms for the formation of ring galaxies. One possibility involves the collision of two galaxies, while another scenario suggests that a smaller galaxy passing through the center of a larger galaxy can trigger the formation of a ring-like structure. Notable examples of ring galaxies formed through cosmic collisions include the Cartwheel Galaxy, the ARP 2026 galaxy pair, and NGC 474. A particularly exciting discovery is the ongoing collision between the Milky Way galaxy and the Andromeda Galaxy. This event, predicted to result in the formation of a new supergalaxy, is named Milkomeda or Milkdromeda. While this collision is a cosmic spectacle, it also has profound implications for Earth. The merging process can trigger bursts of star formation in areas where gas clouds collide, creating new stellar nurseries. These nurseries become the birthplace of massive young stars for the new galaxy. As the galaxies merge, the night sky will transform into a magnificent light show, filled with star clusters, shock waves, and brilliant radiation bursts. However, the effects are not limited to the sky. The collision and merger could significantly impact Earth's environment, leading to changes in temperature, precipitation, and overall climate. These changes could disrupt ecosystems, affecting plant and animal habitats worldwide. Altered atmospheric conditions might hinder species migration, food availability, and breeding patterns, with some species thriving while others struggle to adapt. While this merging event is awe-inspiring, it will not occur overnight. The process is expected to begin in approximately 4 billion years, with a full merger taking around another 2 billion years to complete. Long before that, about 5 billion years from now, our Sun will enter the red giant phase, rendering the solar system inhospitable. The merging of these galaxies and the resulting transformation of the cosmic environment will mark a major shift in the universe, leading to a new galactic structure. Within this new galaxy, there may be star systems with planets in the habitable zone, where conditions could support liquid water, an essential element for life as we know it. However, the stability of this new cosmic structure will be crucial in determining whether life can thrive. Gravitational interactions between stars and the effects of cosmic events could alter planetary orbits and environmental conditions, influencing the potential for life. Although the merging of galaxies will likely increase cosmic radiation and stellar activity, predicting the exact impact on planetary conditions is challenging. If life does arise in the newly formed galaxy, it would likely undergo adaptation to the unique environment. The physical and chemical properties of the new galaxy could lead to a form of life distinctly different from what we know on Earth. However, humanity today would not survive in this new universe due to the extreme changes. The ongoing exploration of the universe over the 1700s and 1800s has led to a reassessment of previous beliefs. New discoveries have driven researchers to lower their estimates of the mass of the Andromeda Galaxy, while simultaneously increasing the mass attributed to our Milky Way. The current understanding is that these two massive galaxies are much closer to one another than once thought. If you were on Andromeda and observed Earth, you'd see a similarly massive world, helping put into perspective the size of both the Milky Way and Andromeda. One thing astronomers agree on is that Andromeda is significantly larger than the Milky Way. The Andromeda Galaxy spans about 220,000 light-years, whereas the Milky Way is estimated to be around 100,000 to 120,000 light-years across. This makes Andromeda an incredibly vast structure, dominating a significant region of space. This updated understanding also highlights the complexities and challenges of accurately measuring the mass of galaxies, especially in the heart of Andromeda. The supermassive black hole at the center of the galaxy exerts an immensely strong gravitational pull on the surrounding stars. As these stars orbit the black hole, they follow circular paths, similar to how planets orbit the Sun in our solar system. When stars pass closest to the black hole, known as the perihelion, they experience the strongest gravitational forces, causing them to move at their highest speeds. This process results in the stars packing closer together and emitting energy in the form of radiation, including visible light and other types of electromagnetic radiation. The intense concentration of stars and radiation in this region contributes to the bright center seen by astronomers, providing valuable insights into the gravitational interactions between the supermassive black hole and the stars. To understand this further, we need to look at active galactic nuclei, AGN, which are highly active regions at the centers of galaxies. AGNs are characterized by intense radiation emissions across multiple wavelengths, from radio waves to X-rays. These AGNs are powered by the presence of a supermassive black hole at the center of the galaxy. These black holes are incredibly dense regions in space where a huge amount of mass is concentrated within a small volume. When astronomers observe the AGN in the Andromeda Galaxy using advanced telescopes like the Hubble Space Telescope, they observe a fascinating phenomenon: two distinct points of brightness. These two bright regions are located slightly off-center from the true galactic core. The brighter region is close to the supermassive black hole, and its luminosity is attributed to the intense gravitational interaction between the black hole and surrounding stars. The mass of this black hole is estimated to be between 110 to 230 million times that of the Sun. Supermassive black holes are common in the centers of galaxies, including our own Milky Way, and play a crucial role in the development and dynamics of galaxies. When matter such as gas or stars gets too close to a supermassive black hole, it forms an accretion disk around the black hole. This rotating disk of material heats up and emits intense radiation across various frequencies, making the AGN extremely bright. Another notable feature of the Andromeda Galaxy is the abundance of globular clusters. These are tightly bound groups of stars that orbit around the galaxy's core, much like moons orbiting a planet. Andromeda is estimated to contain around 460 of these dense, ancient clusters, each holding thousands to millions of stars that formed at the same time. The sheer number of globular clusters in Andromeda provides valuable insights into its cosmic history and its interactions with its surroundings. Smaller galaxies over billions of years suggest that Andromeda has been a major consumer of these smaller cosmic companions, a process known as galactic cannibalism. As smaller galaxies are pulled toward Andromeda, their stars and other components are stripped away and absorbed into Andromeda's stellar population, contributing to the rich diversity of stars found within the galaxy. This characteristic of accumulating globular clusters and stars from smaller galaxies is typical of spiral galaxies like Andromeda, which are marked by their distinct spiral arms. These galaxies create an ideal environment for interactions and mergers with smaller neighbors. Furthermore, recent observations have led astronomers to speculate that Andromeda may be undergoing a fascinating transformation. It appears to be shifting from a typical spiral galaxy into a more unusual form known as a ring galaxy.